Hi guys, it's electronics time again. Today's topic is the popular HC595 shift register chip. I want to see its purpose, how to use it in C, based on an ATtiny 85 microcontroller. What is the purpose of a shift register? Every microcontroller, or MCU, has a specific number of output pins. Especially the low-priced chips like ATtiny 85 and PIC16F often have only a few output pins. Often this is not enough.
Hey, I want to be connected.
With the HC595 it is possible to expand the output pins by another 8 pins.
Oh, thank you.
Another showcase is to use the 595 as an output memory. This has the advantage that the outputs show the logic state uninterrupted as it has been set, regardless if the MCU is busy on another task or while the output is being updated. That is a big advantage if an LED display is used, for example. See here a temperature display with a digital DS18B20 sensor that I've built some time ago. Every time the MCU ports the new temperature data from the sensor via an one-way interface, that's every 10 seconds, the LED display is interrupted for a few hundred milliseconds. It's hard to see on video. With the shift register, the LED display would not be interrupted by this. But how does this shift register basically work? Let's assume that a variable holds an 8-bit value. The microcontroller then outputs this value bit by bit over a serial line to the register of the shift register. For syncing, a clock signal is required as well. Now the value is stored in the register. To transfer this value to the outputs, other control lines are used. If initiated, the value is transferred and the old output value gets overwritten.
The datasheet of the 595.
The control signals are SER, that's the line for the serial data, SRCLK, that's the clock signal for the serial data line, the inverted SRCLR clears the registers. RCLK transfers data to the storage register, and the inverted OE enables or disables the outputs. To put the chip in action, I need a C program. After some search, I have found an example code on the web. Okay, and that's the code I found on the internet. Yeah, that's not the URL where I found it, but I think you can find it there. And yeah, it's originally intended for the ATtiny 13, but I will use it on the ATtiny 85. These two chips are not too different. The ATtiny 85 has just more memory and stuff equipment on board, but the basic structure is the same. And yeah, 1 MHz clock is fine. And that's for the avr.gcc compiler. That's fine because I really like this compiler. And why do I like this compiler? Well, it's free and it gives really nice code. That's pretty efficient. And yeah, this code is intended to control a 74HC595, so that's our shift register, hooked to 8 LEDs with some resistors, but yeah, I want to use it in a slightly different way. These LEDs are inside a 7-segment display, but that shouldn't matter here. And yeah, let's have a quick look here on the code. So that's where the 1 MHz clock is defined for the delay routines. And the I/O header is important for the pin names, and the delay age is important for the delay functions. And here we define which names assigned to the corresponding pin. So the data pin is B0, enable pin is pin 1, latch clock pin is B2, shift clock pin is B3, reset pin is B4. So we have 5 control lines. So that will mean that all available IOs are blocked on the ATtiny 85, but we gain 8 outputs via the shift register, so that's okay. And maybe it's even possible to omit one pin, but I haven't checked that. I'm really new to this shift register chip, but maybe it's possible to omit the reset pin, because it should be possible to shift in just zeros, and after we have shifted in 8 zeros, the chip is basically resetted. But I will hook it up that way here, just to be sure that it will operate properly. Let's see, here the forward declarations of some functions. And there we have the main. All outputs are set as outputs. All I/O pins are set to outputs, to be correct. And then we have this array here with 8 individual digits, and we have a 1 in the front. The rest is 0. Okay. Okay, here's the while loop. Okay, and it gives us 2 options. Option 1, readout array from position 0 to 7, and latch the display as each bit is shifted. So the display shows the scrolling effect and utilizes the fact that everything is in the shift register shifts over when the new bit is latched. Okay, so option 1 is simple, command this, command blah blah. Okay, that's fine. Let's see what's option 2. Read 8 bits from the output array, iterating through the starting positions 0 to 7 and wrapping around the array to include all 8 bits in output. Once there are 8 new bits shifted into the shift register, the latch pin is toggled, and update the display. This option will yield the same result of the display, but the loop is effectively doing the scrolling, not the shifting of the register like in option 1. Okay, I think I will stay with option 1. And let's see what he does there. There's a for loop, starts with 0 up to 8, increments on every cycle. The corresponding part of the array is output to the register bit, to the data pin basically. That's port B0. And then he calls the function shift in. After that, latch in. Let's see, shift in, latch in. So here's shift in, and what he does is he sets the clock pin high, and after that he sets the clock pin low. So that is one shift in step, and he implemented delays here, and delay 20, I've seen it at the beginning, that's 20 milliseconds. And these delays are arbitrary. They are here to slow things down so you can see the pattern. Okay, that's nice, because otherwise it would be too fast to see it. And the latch in, it's basically the same. He sets the latch clock pin high and waits 3 milliseconds, and then he sets it low again, and again waits 3 milliseconds. So then the corresponding bit is set to the output or shifted to the output. So we can see it at that moment. And okay, you have a reset shift register. Yeah, okay. So that's the reset function. I think then all registers are set back to 0. Okay, yeah, let's jump to the Microchip Studio. The code is already here. Yep, all is there. Okay, let's see if it's compiling properly. Yes. Okay, compiling succeeded. That's good. Okay, so that part is done. Now I have to build the circuit on the breadboard, and I don't want to bother you with the build-up process of that breadboard there. The next thing will be flashing the code. Okay, for programming, I use this tool here. It's called ProgISP172, and yeah, that works fine with my USB ASP programmer. And I already loaded the corresponding file. And yeah, then chip erase is activated, that's okay. Blank check, yes. Program flash, verify flash, and program fuse, that's okay. Let's see the fuses. That's okay, that's okay. Divide clock by 8 internally, that's important here. Then we have 1 MHz clock. And yeah, internal RC oscillator with 64 milliseconds of startup time, that's fine. No memory lock features enabled. Okay, that's good. Then I can click auto here and you see he's programming. And yeah, erase, blank, write flash, verify flash, write fuse, successfully done. Great news. So, that's the breadboard. I made all the connections here. And you see, it's a lot of them. And yeah, let's first see, that's the ATtiny 85 here. Yeah. And from there, go to the shift register chip. And from there, we go to the 7-segment display. And of course, there are some resistors in front of each individual segment. And yeah, what is really important, I made all the connections from the ATtiny 85 to the shift register according to the program. All 5 lines are connected. And what's also really important is that I connected the outputs of the shift register according to the names of the 7-segment display, because each individual segment is named by a character like A, B, C, D, E, F, G, and the outputs of the shift register have also names like QA, QB, QC, QD, and so on. And I just connected it accordingly. This should make it easier to make the 7-segment display running accordingly, properly, that it shows proper numbers and not some garbage. But anyways, now I want to see the cycling of the LEDs. For this, I have to connect power supply, ground to ground, and plus to plus.
And yeah, that's great news. It cycled through all the segments here. Let's have a closer look. Yeah, isn't that nice? That looks really funny. And yeah, on camera, the red is not as red as it is. In real life, it's really, really a nice red color. Yeah, but anyways, the code works. The connections are right. So the only thing now, or the next step now, is to change the code that it displays proper numbers here. And the plan is to display numbers from 0 to 9. So let's do that.
And when we have a look on the datasheet of the 7-segment display, you see here that the segments are numbered as A, B, C, D, E, F, G, and DP for the decimal point. And yeah, I have added a view of the pinout, but the pins are on the bottom side. We are looking from the top side here. So yeah, that made it easier for me to make the right connections on the board. And I have just assigned the pins accordingly. You see here, that's the pin node from the HC595 with its pins, output pins from QA to QH, and yeah, the 7-segment display with A to G, DP. Yeah, okay, I haven't connected that DP, so forget that. Yeah, but they are connected accordingly here. And the numbers, for example, the 0, needs to be picked out from the data sheet. For example, for the 0, we need to have the segment A, B, C, D, E, and F active. Just the segment G is not active. And usually that would be exact the same bit number. But there's one special thing about the shift register, and that is that the output byte, if you so will, the output byte is reversed to that what you have shifted in. And you have to consider that. And that's why the numbers are reversed. You see that the last digit is always not here, should be all the time 0, because I did not use the last bit. That could have been the decimal point, but as I don't use it, I haven't connected it. And you see that then the most significant bit, the 0 exactly after the B, or directly after the B, that this is 0. And that is because we need to have the G segment inactive. But as you remember, usually it should have been the last bit, or one bit before the least significant bit, but it's all reversed now. Just keep that in mind if you plan to use it. And I picked out then the bit pattern accordingly, and that's what I have copied into that array here. That's exactly the same. And the for loop then picks up these elements and yeah, shifts it out. That's it. Yeah, I already inserted it, the program, into the Microchip Studio, and we can see that it should, it compiles without errors. That's good. Then I can again use proc ISP. I already loaded the flash here. It is loaded. The settings here are the same. And now I can program it. But first I have to reconnect the breadboard.
One eternity later.
The breadboard is connected and now I can program it. Okay, that was successfully. So now I can test it out if it works as intended.
Okay, as the code is now flashed, now let's check if it works as intended. Again, I just have to plug the power in. Let's see, ground on ground, and plus on plus. Yeah, it works. Good. It counts as intended from 0 to 9. That's so nice to see. Oh man, I really love these 7-segment LED displays. They are very good visible and give a good contrast. It's like the tiny brother of the OLED displays. Okay. So that's great. The goal is achieved, and if you're not already a valued subscriber, you have now the chance to become one. Stay tuned for more videos and take a look on my product links in the description, and please consider to make a donation that I can keep up with making videos. So I will see you next time. Bye bye.